Okay, let's have a look here. Alright, I think with this we should be just about live here. We have this time, so let's just start from the top here. Yep, so welcome back again to another live stream for the Lab Coat Math channel. As always, you should be able to send in your any requests you have down to that left side directly to the email at labcoatmath@gmail.com. Anything like that will be answered up front, but we should have everything we need to start going forward on this. So we have the 2016 free response questions. Again, there are 6 problems. We'll go through all of them, and 2 at a time is where we will go and go over the questions and all of these steps to solve these types of problems. Right? That reminds me, I do need my graphing calculator. We're doing this a little bit out of schedule here, but we should have everything ready to go. So we have our graphing calculator that will be gone through, and make sure we have this all set up here perfectly so you can see my face going through this with the lighting here. Make sure it's like that. Okay, very good. So we have our calculator for the first 2 problems. The rest of the 4 will not, out of the 6. And as usual, I'll be doing things on my notebook directly, and we will have all the questions on there, and we'll be going through every step of the way for this. So let me go ahead and get my trusty pen here, and make sure we have the red pen on handy as well for the corrections. Okay, very good. So this again is the packet, the 2016 free response. We'll go through each question on this, as you can see here, and if the camera can focus, there really should be enough lighting for this to focus up properly, but for whatever reason, okay, there you go. All right, so again, all the things will be on there, and I will go and usually copy down the parts that are on there such that it will be easily seen on the notebook. So without anything further stopping us here, why don't we go ahead and get going here. Yeah, I did get some advice that lighting is part of the reason why. Let me see here. We can get just a little bit of light on both the face and the notebook. I think that should make everything much easier that way. Okay, good. So let's start with problem number 1 here. We have a table of T and R of T, and we'll fill that out. Okay, 1340, 1190, 950, 740, 700. Okay, and the problem itself says that water is pumped into a tank modeled by W of T this time is equal to 2000 times E raised to the negative T squared over 20. Okay, and this can be liters per hour for the interval from 0 going to T to 8. Okay, and then T is in hours. Okay, and then it says water is removed from the tank modeled by R of T, which is in liters per hour. Okay, and then it's also decreasing. Let's see, which is decreasing from the interval from 0 to T to 8. Okay, And then yeah, the table that's already there. And then also at time t is equal to 0, there are 50,000 liters of water in the tank. Okay, so our first step here is that we will then estimate for r prime of 2. Show the work. That leads to your answer. Okay, so hopefully with the way that my writing has been since we started stream, hopefully this should be at least legible enough for the most part until we can get a better solution here. Alright, so r prime of 2, so we're doing this an estimation of a derivative of a function that we only have tables for. Again, this is going to be average rate of change that they're solving for. And that will include this equation of, because we want to find r prime of 2, we can simply look at 1 and 3 and see what that changes in between the two, and that'll be a good estimate of r prime of 2. So with that, it'll be r of 3 minus r of 1 all over the differences in the time values, is 3 minus 1. And then we just simply do a plug-in of 950 minus 1190 all over a positive 2. And this one should not require a calculator, given that this is very simple algebra that we're working on here. So this will be a negative 240 over 2, which is a negative 120. Now, in terms of the units that are going to be part of this here, is that we will need, in terms of his liter per hour, that's what r of t already started with. Then, if we were going to go and do the average rate of change of liters per hour, that will be liters per hour squared, because, again, there's another time factor of hours in the denominator from the numerator, which already has liters per hour. Some very simple unit conversion, and so that will be the answer to part A. Okay, going to part B. Now this is something that I have been doing quite a bit on our video series until just recently when we have concluded that. It says here to use a left Riemann sum of 4 intervals, or sub-intervals, that's a better word, sub-intervals on the table to estimate the total amount of water removed during the 8 hours. Okay, so that's not too bad for itself. Okay, but they continue to ask, is it an overestimate or underestimate? And we need to obviously give a reason for that result. Okay, so because we're doing a 4 sub-interval sum here, that would mean that we're going to go about this in different ways. So we have the connection from 0 to 1 as our first rectangle, then 1 to 3, 3 to 6, and 3 to 8. So those would be the 4. We already have 5 points that will span across all 8 hours. But of course, there's our note here is that not all bases are the same. All right, that is something that we would need to take apart of our time to understand, is that because the bases of these rectangles are not the same, it wouldn't be such a smooth of an addition problem, but still the area should come out nonetheless if we just take each one individually. So because we are doing the left Riemann sum, again, that means that we have to take the left answers of the 1340 as one of them, and then 1190, that is, and then a 950, and then 740, and those are the 4. Again, this is a left Riemann sum, so the 4 on the left are the only ones that matter. Okay, it's because of that. Now we have to look at the bases for each of them. So the 1340, that's kind of a base of 1. The 1190 has a base of 2. The 950 has a base of 3, and the 740 is a base of 2. Remember, we were looking at the connection between each pair of points, and we just take the left one, but the base will be the difference between the values of t on that matter. So we just simply have to add everything up here. So that's 1340 with another 1190 times 2, so that'll be 2380. And then 3 times 950, that will give us 2850. And then lastly, 2 times 1740 will give us 1880. Or, sorry, 1480. My mental math has not been showing up as well as it should be. But with that, we should add everything up. I'll double check with my calculator nonetheless to make sure that it's all there. But at least in this case, we end up with, let's see, carry the 7, put up a 2, 10, 7, and that makes it exactly 20. And we carry a 2, so 6 and 8. So 8,070 liters have been removed. Again, because we took the area underneath a rate equation, we would then have just the volume left. So let me quickly run this through on the calculator. Hopefully it's visible here. It's a little bit hard to see that. We don't want to tilt this, but okay, maybe that should be better. Put it that side. Okay, so we just got to add everything up here. So we have a 1340. Well, that parentheses didn't really matter, but let's see, and then 1190 times 2, and then we have the 950 times 3, and then lastly 740 times 2 again. Okay, so that is the addition of all of the rectangles there. 8050, 8050. Interesting. 1190, 340. Let me make sure my parentheses are all there. Make sure we have to insert. Insert the parentheses correctly there. Still 8050, 740 and 2. Something is seriously not adding up here. I want to make sure that everything is good here on that aspect. $50, 80, 80, and a 40. 12, 30. Whoa. What is happening? That is supposed to be 80, 50. Well, the mental math needs to have better faculties. Thankfully, the calculator kept us in check there. 8,050 liters removed is indeed the correct response there. So that should be it for part B, using a left Riemann sum. Then part C is saying, let's see here. So use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so we have a little bit of a setup to start with here, because we have two different things that are being asked for. So we want to know, again, from part B of the month that's removed, we need to see the total amount at the end of the 8 hours. So we have multiple things going on here. Obviously, what they stated at the very beginning of the problem is that we have 50,000 liters to begin with, and then we also have the model of water being pumped into the tank as well. So there's three things, right? So there's going to be the starting water, and it's going to be added with the pumped in water, and then lastly we need to subtract the removed water, which again, this removed water part is going to be part B as our answer earlier. Okay, so with that, let's see, I wonder if there's really anything I can do about my face constantly being in a shadow thanks to the lighting. Okay, so with that, we then need to start plugging things in. So we have starting water at 50,000 liters. Now the water pumped in, though, that itself, because they gave us the function of the rate of the water that's pumped in, we just need to go ahead and put in the integral. Now going from 0 to 8 hours for the W of t, which in this case, respect to time, is going to be an integral from 0 to 8 for 2,000 multiplied by e raised to the negative t squared over 20. And we subtract it with the removed water, which we've already found in part B, which is the 8,050 liters that are removed. So with that, this is exactly everything we need to plug into the calculator. So let's have a look at what that will be like. So for me right here, what I prefer to do is that we have the 50,000 that was already there. And then, okay, Arum Amir Khan has a retracted message. We'll have to see if he has something to say since he entered in this chat. Everyone is welcome here. Any sort of questions can be sent directly through the chat or through the email on the bottom left. And if there's anything we can help out with, we can definitely do that. In the meantime, we're still working on this calculus section here. So, in any case though, we have our part here, the 50,000, and we need to subtract it from our part B answer, which was the 8,050 liters that were removed during the time frame. And then lastly, we need to, if I can make sure to put that in properly, 8,050. And we need to then add it with our integral here. Again, using function integral as part of what my calculator can do. But with that, we then have to just put in the equation. So it's 2,000 times e raised to the negative t squared. Let's see, t squared. Okay. And then from there, it needs to be divided by a whole 20, and that will close off the entire exponent. And then we'll be telling the calculator we're integrating off the variable of t going from 0 to 8 hours. Okay. So with that, it'll run the calculation and we end up with 49,786. They said to round to the nearest liter. So it's just going to be 49786 liters as the result of this integration. So that's 49,786 liters that are left in the tank after 8 hours. Okay. So we have all of that there. So that will be part C. Then we should finish off with part D. Okay, so it says here for the time interval going from 0 to t to 8, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank. And we would need to explain on the same about that. Okay, so for this again, they're asking at which there's a rate the water is leaving, again, is being removed from the tank. Alright, so because of that, we're going to need to do some good old mean value theorem, looks like. Or actually, it's not mean, it's going to be intermediate volume theorem, because we're trying to prove a specific value in between the values that are already given. And they want to see if they're going to be the same at any time. So both are, in terms of a note that we must make, WT and R of t are going to be both continuous. So that's a good help for us as to what we can conclude based off of that information. But they want to see if WT and will be equal to R of t at any time where we're going in between 0 and 8 hours. Of course, given that this is a calculator section, we could very easily then try to see at times at which they will be either equal to each other, or again looking at the ends for the types of problems that we have. Again, if we look at the end parts, and because they're continuous, they need to at least cross each other at a certain point. Okay, so because of that, we have the R of 8 and R of 0. Okay, so the endpoints there of those two, again, is be 1340 and then 700 liters per hour on each of them. And then for W of 8 and W of 0, for those parts, we can then plug those in directly to the calculator. So we're going to have 2000 times e raised to the negative, well, it's just 0 for the first part, which will just be 2000 at W of 0 liters per hour. And then W of 8 will be a negative 64 over 20 in the exponent. So it's going to give us 81.522 liters per hour. So they will cross at least to some point over each other because of the way that they're both continuous, and they will have to cross each other's paths at a certain point. Okay, I actually believe that this is actually by squeeze theorem in that sense, but because they're both continuous, right? We have a yes, we will know a t exists. They didn't ask. Remember, they didn't ask exactly what that t is. They just want to know if it is possible. And because we have a decreasing r from 340 to 700, while w is increasing from 81 to 2000, they will eventually have to cross each other at a certain point. We just don't exactly know where. But where the wt and r of t exist, rt are equal to each other. Again, it's because of IVT. Again, we can prove that they will, at some intermediate value between these two functions, that because they're continuous, right, that t will exist. Okay. We have that to prove it for us, and that should conclude it for problem number 1. So we still have a few more to go with to go through problem 2. So again, there's all 4 parts to problem 1. So I'll flip this over to problem number 2, and we'll see how that goes before we start checking our first 2 answers here. Okay. So problem number 2 for us shows itself right here. If I can get everything arranged properly, please. So we have problem number 2. Okay, it says here for t being greater than or equal to 0, a particle moves along the x-axis. The velocity of the particle at time t is given by this equation. So v of t is equal to 1 plus 2 times the sine of t squared over 2. The particle is at position x equals 2 at time t is equal to 4. Okay, so part A says at time t is equal to 4 is the particle speeding up or slowing down. Okay, so our first problem already of part A, we have the velocity and they're asking up for a speed up or slow down. So something that we need to take a quick note of for ourselves, given that we are talking about the speed of any given particle, is that then speed up and slow down is that we need that relationship between velocity and acceleration. We need both in order to determine the speed up and slow down because, again, with velocity and acceleration, we're looking for same sign on the velocity and acceleration. So again, if they're both negative or both positive, again, with that connection, then that will mean it's a speed up for us. And then a slowdown is in that case if the velocity and acceleration are opposite signs. In that case, that will indicate a slowdown because that is going to tell us the direction at which the speed is going based off of what we have for the both of them. Okay. So because of that, we first need to then discover what the acceleration function is going to look like. At least for us, means that it's a derivative of the velocity respect to time. So by doing that, we will then just go take the derivative of that equation, the 1 plus 2 times sine of t squared over 2. And so that will give us a 2 times a cosine of t squared over 2. And then chain rule will follow afterwards. We need to take the derivative of the inside of the t squared over 2, multiplying by a full t because the coefficient rule will cancel. So to clean that up just a little bit more so that everything is clear for us, we have a 2 times t times a cosine of t squared over 2 as a result for our acceleration function. Okay, but even with that, they're asking for a specific time of t is equal to 4. So we need to find that accordingly to discover what that looks like. So at v of 4, we have a specific answer here, which is going to be 1 plus 2 times the sine of 4 squared over 2. And then on the other hand, we have the acceleration at 4 as well. So that'll be 2 times 4 times the cosine of 4 squared over 2. So we can plug both of these directly into the calculator in order for us to find that out. So we can do that straight away here. If this will be a correct angle to see that. Yep. All right. So 1 plus 2 times the sine of 4 squared over 2. So that guy turns into 2.973, so 979. So 2.979 is the velocity. And then the acceleration is going to be a little bit different. That'll be 8 times the cosine of the 4 squared over 2. So that instead gives us a result of a negative 1.164 instead. Okay. So because of that, we have a different sign. It looks like we have a positive sign on the velocity, negative sign on the acceleration at time is equal to 4. Therefore, the particle is slowing down at the time of 4. So that will be the result of our first part of part A, and we'll move onwards to part B. So it says here to find all times of t in the interval 0 to t to 3 when the particle changes direction. Okay, so they want a directional change evidence here on that particle. So because of that, if we're looking for change in direction, that is going to be where the signs change on the velocity graph, because velocity sign as a positive or negative, again, any sort of switch in that manner will then indicate for us a direction change for us. Okay, sounds pretty good for us. So let's have a look here. With the velocity and going from just from 0 to 3, we would need to go to the graph here for us to understand that. So we can set that up very quickly and we'll see what we have to offer on that. So on our graph, we can clear that out from our previous. So we just plug in the velocity function, which is just right there over at the top. So that'll be 1 plus sine of, let's see, x, so we have to switch to x because we're graphing here. So x squared over 2. And that will be the result of that graph. Let's make sure we set our window properly. We will need to go from 0 to 3. So let's go from -1 so we can see the axis all the way to like 5, just so we have everything there. Plus or minus 5 should be fine. We just want to look any sort of changes here of crossing. Okay. So this is a little bit interesting because it does not seem like we have really been crossing any of the they gave us a position at a time, but that does not matter right now. We're just looking for a change in direction. So let's have a quick look at the, let's see if we can trace here a 0 at some possible locations here. So at the left side of the curve, let's go with that. And then the right side, something like this. So do we cross a 0? Or do we actually cross multiple? Okay. Yeah, it looks like we crossed multiple. Let me make sure we're looking at the same thing here. Because that's very close to 0 right there. But maybe we need to start doing a better table set here. So the change in table, let's do it 0.1. So let's have a look at that table again. So going down, we get closer and closer to 3. At 2, and then going to 3. It does not seem like we're getting anywhere where we need to be on that graph. Right, because in order for us to get to a -1, we need to get to 3 power 4 if we wanted to do that. Oh, 3 power 2. In terms of that, yeah, we need a 4 inside. But I don't think we're not getting that. Almost a 5. 9 over 2, 4.5. 9 over 2 is 4.5, so we can't even get there. I think bigger than -0.5 will take us over. It's a little bit confusing here, because the way that the graph is showing. I wonder if we just take a look closer here. Because we want to take a zoom into that section right there just to make sure. Again, I want to make sure we're taking the time that we need to do absolute certainty of what we're looking at here. So let's get closer here instead of, let's go to +2, go between 2 and 3. And yeah, so what happens if we took all that space up just to have all of absolute certainty that we have not crossed the axis? Have we even crossed a 0 because of that? Let's see here. So let's get very close here. Let's go a little bit. Let's go at 3. Do we cross at 3? No. There's not even a single cross of the particle at all. Make sure we're doing this. So 1 plus sine of x squared over 2. It's 2 times. That is why we need to really make sure we are putting everything together in the most careful of senses, because that did eat up a little bit of time because of that. So let's go back to -1 to, let's say, 5. Sure, let's graph it that way instead. I had a feeling it should have crossed. It might have crossed twice even. Yeah, okay. So that's very good. So let's start tracing some zeros then. Now that we've done that properly. So left side, right side of that. So we have one cross here from positive to negative. So let's make sure we have that showing. So from positive into a negative on the number line, that's going to be an x value of 2.707. And then let's check that other guy though. Left side of u going to the right side of that. So with that part of the graph, that is going to be a 3.39 4. Back to positive again. So there's only one that's underneath 3. Again, they specifically asked for the interval going from 0 to 3. So there can't be anything more than that. So only one part. So one time at t is equal to 2.707, where the particle changes directions. Changes direction in the interval from t going to 0 to 3. So that's the only point in time, thanks to the graphing calculator, once we actually put it in properly, that's what it looks like. Okay. That took a little bit of time, but that's all that we need to do to make sure that we're very careful as to how we are putting all of that together. So next it says to find the position of the particle at the time is equal to 0. Okay. Now we want to find position. Thankfully though, we already are given a position specifically at a given time here. And one thing to note is that at the x of 4, it said that it was at 2. That's from the problem. Okay. And again, any sort of indefinite integral from the velocity respect to time will give us our position plus a c, given that it is a indefinite integral because of that. Okay, but because we know one point and we want to find x of 0, and make sure the volume of our song changer is not killing us, let's make sure we put that down a little bit more. Okay, I think that's a bit better. So in that case, we can just set this up as a definite variable using our good old friend, the fundamental theorem of calculus, knowing that if we go from 0 to 4 on the velocity, then we will get the functions of the position from 4 minus x of 0, which we already do know x of 4. So we just need to do a little bit of algebra to swap things around. So x of 0, we can then go ahead and say that it's going to be instead x of 4 subtracted by the 0 to 4 integral of v of t dt. And we just need to move that over, and then we just need to keep a negative on there. The negative needs to move over as well, and that would result in the x of 0 being isolated on its own. So because of that, we have a 2 as a result from that point, and then we can solve for the definite integral from 1 plus 2 times sine of t squared over 2 respect to time. And so that results with the point exactly what we need to be. So let's go ahead and put that into our calculator here, and we should be able to be home free after that for that part. So that's going to be 2 plus 2 minus, that is, sorry. It's a subtraction. 2 minus the integral, this time of 1 plus 2 times the sine of, this time, t squared over 2. And we are taking this for the variable of t, going from 0 to 4. Alright, so with that, it will calculate as a negative 3.815. Okay. So negative 3.815. Does that actually make much sense for us? This is going to 4. Oh, because we're subtracting by it, of course. Yes. That's why. Yeah, no, that does make sense to me, at least to that sense. Okay. There you go. And that will be the result of that problem. Okay. Then for part D, it says for us to find, let's make sure we have this all centered nicely for the camera here. Find the total distance. The particle travels from t is equal to 0 to t is equal to 3. So total distance, though, that's a little bit different because if it's just start to finish, that will be exactly what the integral was asking for. So again, something to, if you want to take a note on this, right? Okay, it's just, if it means just displacement, again, which is just going to be start minus finish, that result is just going to be the integral going from 0 to 3 for the function v of t dt. But we don't want that. That is the trap that they set up for us on this problem, because for those that do know that if you want total distance, that means you must count all of the negative parts of this of that distance that was traveled into a positive. So again, we need all positives inside of the integral, which means in our case it's going to be from that same interval from 0 to 3 as the limits, but this time it will be the absolute value of v of t dt. Now that will be the proper response to this integral. Okay, so because of that, let's see if our let me double check if my yes, I do have an absolute value mode. So let's see if that will go ahead, because this should be all done, able to be done in the calculator. So in that case, if we did our integral this time going from 0 to 3 of the absolute value of 1 plus 2 times the sine of t squared over 2 of dt, and then all that is in the absolute value, we can go ahead and see if that will all be nicely fit into our calculator here. And it needs to really be on this side to show. Why don't we just do something like this? This is really where it hits best, looks like. Okay, so let's go ahead and hit the absolute value this time, but now we're gonna go and try to flip this over so that's the absolute value as well of all of that our guy. So 1 plus 2 times the sine of t to the second power over 2. Okay, so with the absolute value, we're still going to tell it that we're going with the variable of t going from this time 0 to 3. And if we throw that into that, does not like that. Okay, so let's have a quick look here. Does that? Ah, it's because I did not insert the right number of parentheses. There you go, let's try that. And with it running its little thing there, you can tell by the very, very slight crawl, if you can kind of see that. It's a very, very small crawl. There you go, now it shows. Alright, so it took its time, but we end up with 5.301 as the total distance. That's why absolute value is very important for these types of integrals, because integrals do calculate negative area, as you can see in our previous graph here. It would have calculated a negative area between those spots, which is not what we wanted. We want to make sure that everything is flipped and considered in the positive sense, which is why the absolute value was important. Okay, so that is part D for problem number 2. So it looks like we have our part here finished, and we will be able to get back to seeing if how the answers will hold up. So I'm going to swap to my red pen here, and we can go back to problem number 1 to see what the results of this really are. So just as a quick reminder, this is what I will be looking at, although we will be back to the notebook again, but still, this is what I'll be looking at in terms of what the problems will look like. So it's in 2016 right there. So going to this end again, there is the scoring guideline with all of the answers to the questions, and we'll see how that holds up for ourselves. So let's go back to the notebook again. So with problem number 1 here, it does say that negative 120 liters per hour. That is indeed correct. And then the estimation using the with the right units, that's going to be the correct part. So the estimation and the units being all correct, that's 2 out of 2 correct for this part for me. Okay. Then for part B, using that left Riemann sum, 88,050, that is correct after a little bit of mental math flubbery from my side. But doing the left Riemann sum and setting it accordingly is important, actually getting the correct estimate. And I did not state whether this is not over an estimate. Okay, so stating an estimate over or under. I completely forgot to do that, so that is only going to be 2 out of 3 points for me on that question. That's unfortunate. I need to make sure we keep on the task of making sure we answer all of the questions. So part C, though, will continue, is that we will then end up with the integral going from 0 to 8 for WT. Again, all set up with the integral. That is a cause for a point right there. And then the estimate of 49,786. That is exactly correct as well. So that's 2 out of 2 correct for me. And then lastly, we have the W of t here. So given that they're both continuous and the intermediate value theorem does guarantee, so considers that subtraction that they are going to be equal to each other, and then with the IVT there will be at least it does guarantee at least one of them. Good. So both of them will be correct for that part. So this page has 8 out of 9 points. We'll go back to that in just a second. I want to take a note on the front of my quiz just to make sure that will make it a lot easier. So here we go. So question 1 is 8 out of 9 points. So going down, and again, this is how I will keep track of all the points throughout this packet. So there's 6 problems per FRQ packet, and we'll add them all up once it is all over. Okay. So with that, let's go over to question number 2, and let's see how that holds up. Question number 2 will be right here. And let's take a look here. So first off, we have the slow down, because the velocity and acceleration do indeed have different signs as that we have proven. So this is 2 out of 2 correct on part A. Then for part B, so we have all the times at which it changes direction. So there's only one time indeed, the 2.707, at least between that interval that they asked for. And so we do show that it's from the graph on that point. So 2 out of 2 correct will be the case for this as well. Okay. Then for part C, we are looking for the position exactly. So the integral needs to be set up here with the x of 0 being isolated, and that shows as a positive. Why does that show as a positive? Oh, because they swapped the, okay, they swapped the limits. Okay, no, it doesn't matter. No, this is correct. And they kind of got me there, but that doesn't really matter for this. They swap the limits on their end to make it a positive, but it'll literally give you the same exact answer. So the correct setup is already there. Initial condition, of course, that they talk about, that's what they wanted you to bring up into the attention, which is shown here in the work as well in both cases. And so the answer of negative 3.815 is indeed correct. That is 3 out of 3 correct for this part as well. Okay, and so if our camera can focus on this, please. Easier. Hello. Yeah. Okay. All right. So, and lastly, we have part D here. So they want a total distance on this. That it will be indeed the absolute value of v of t going from 0 to 3 to 5.301. That is indeed correct as a total distance. The integral setup and the answer, that's 2 out of 2 correct. So this whole page gets a total of, so 9 out of 9 total on that part. Okay, so I'll take a note on that on our question 2 record here, 9 out of 9. Okay, so looking good so far, but let's get back to what they were asking for back in question, that is question number 1. Okay, so let's see here. My phone is popping off for whatever reason. Oh yes, one of the very classic, looks like that has been coming around for a nice scam for our money off toll roads out here in the West Coast. Isn't that wonderful? But nonetheless though, we still have to deal with this. Let me swap to a color to show that we are doing a correction here. Then just a note off to the side. I wonder if, will this show properly? I know colors aren't exactly the best thing on this camera, but if we show, let's see, this. Oh, well, I have to write a little bit more clear, but I think this should show directly. So they were asking for an over or under estimate on this, on the whole left sum on this part. So it already gave us that we have a decreasing sort of function here. Okay. Now, while it's decreasing, though, we do have the actual average rate of change here, that it's also decreasing. So again, we are decreasing and concave down. Okay. For this set of parts here. So because this Riemann sum is going to be on both of that, again, we're on that lower side of things going downwards by choosing the left parts, as you can see, on a decreasing function. That means we get to have an overestimate. Okay. And that can be easily seen as well. So because this is an overestimate, it can be easily seen because we chose these 4 left turn parts of the equation. Again, decreasing, it's going from starting down to lower, but then instead, if we went the other side of 700, 740, and then stopping and not including the 1340, that would mean that it is an underestimate. In this case, because we are decreasing, so we start at a high number and we take that into account and we cut off the lowest number versus going the other way around of we including the lowest number and cutting off the highest number, this will indeed be an overestimate of the value, and that is what they were looking for in part 2 of this test. Yeah. Okay. So because of that, that was 1 point missed, but as a good reminder to keep up with the attention to detail here for ourselves on this part. So because of that, we should have everything good here. No other corrections need to be made. And there are no other questions that are stated in our chat just yet. But that should leave us to get over to problem number 3. So problem number 3 means that our calculators we put away, this is no longer needed for the rest of this test here. So again, problems number 3, so 3, 4, 5, and 6 are all not needing of a calculator, so we will not use it. And let's get over to problem number 3. So problem number 3 looks like something like this. So I'll copy the graph over so we have something to refer back to, and we'll get started on this. So let's have a look here. At problem number 3, we have the graph going from 4 to -4. So let's make sure I keep that something like this. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, and 4. And we need to go all the way to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay. So let's start plotting some points here. So -2, 0 is good. 0, +4, 2, 0, 4, +4, 6, 0, 8, -4, right there, okay, and then 10, 0, and then 12, -4. Okay, so because of that, we can go ahead and start plotting these points into filling it out into a nice graph for ourselves. This will continue down and dip like that. There you go. Okay, and this is the graph of f for that case for ourselves. Okay, and so with that, it says here, and so it says here as context, again, this is from -4 to +12 for x interval. Okay, and then we have so f is a piecewise function. That's another bit of information that they give us. Okay, and then g of x is defined as a different equation as the integral going from +2 to x of f of t, that is f of t dt. Okay, so we have all of that listed out for us. So for part A, it asks us now, does g have a relative minimum, a relative maximum, or neither at x is equal to 10? And justify your answer. Okay, so we have all of that put into there for us. So let's see if we can prove that we have min, max, or neither at x equals 10. Well, this one looks like is exactly the problem that I literally just made a video about today. How very convenient. Because if we want to find g of x's mins or maxes, that must mean we need to take the derivative of g in respect to x. Right? So this guy, that derivative in respect to x is going to be, in this case, the exact derivative of the integral that was given to us earlier in the problem. And that is exactly partly why we need to understand fundamental theorem of calculus down to the very bones here. Because this results in the derivative of g resulting in simply the function of f of x. No plus c, no need for the lower limit. Again, for those who truly understand the fundamental theorem, is that they would have to see that we're only dealing with just the f of x as a result of the limit with only the variable going inside of the derivative here. Okay, so because of that, we have this to deal with, and of course we need to go back to our number line analysis to see if we have at x equals 10 here. Again, they want at a very specific point, x equals 10, that was asked for in the problem. Is that going to be a min or max to start out with? Okay, so at x equals 10, we have the point up there because it ends at 12, so this is the 10, 0. That was up there on our graph of f to begin with. And because it's 10 comma 0, but if you look at, we are negative before that section approaches, and then we are actually negative again after that section as well. Would you look at that, having negatives on both sides, even though you hit a g prime of 10, even though that was equal to 0, but because we hit negatives on both sides as part of our analysis, that would mean that at g prime of 10, it is neither a min or max for g of 10, the original function that they asked for in the beginning. Okay. Again, our work will show for itself that we see that it is negatives on the first derivative for g on both sides, making it neither a min or max. We need a change in the signs, and we have not gotten that. So that will conclude that it is neither in that case. Okay. Again, as a quick reminder for anyone that is still watching at this point, again, you can send all of your questions to the email down at the left side of the screen, the labcodemath@gmail.com, or again, any sort of shoutouts in the chat hopefully should be answered as we go through all of these parts together. Okay, I think we should definitely have a lot more to go through. We're still on just problem number 3 on the 2016 AP Calculus free response questions. So if there's nothing else to hold us back here, we will definitely continue. So question B is asking for, does the graph of g have a point of inflection at x is equal to 4? Okay, we need to justify as to why. Okay, so let's go ahead and have a look at this. A point of inflection for g, that would then mean that we are dealing with a second derivative, right? So now the second derivative of g needs to be looking at some zeros, again in this case for the second derivative at 4. Okay, but of course second derivative then would mean that we would just need to take our first derivative and go one more step further, which means it's the first derivative of f in that case, and that would mean at the first derivative of f of 4, again, what are we dealing with? All right, so at 4, if we go look back at our graph at the start of the problem, is that there has that point of 4 comma positive 4 as shown in the beginning of the problem. Okay, but what does that mean though? That for that part, if we do our number line evaluation here, is that for the at the spot of x is equal to 4 for that function, well, as you can see, we are, again, because we're looking now at the first derivative graph of f, not just the actual graph. Again, we are increasing and then decreasing. All right, that's how we know the signs are going to be for that, right? As you can see, it is increasing as we approach to 4, and then it decreases right afterwards. So because of that, we have that result, and that is indeed the change of sign that we are looking for. So the function of g at x equals to 4 has a point of inflection. Okay, we have proven that with our work of understanding what the second derivative of g looks like and what that means for us in terms of points of inflection that was asked. Okay, very good. So we will continue forth to part C here for this problem. So then we'll ask us here, so it says find, we can straighten that out. Okay, it says find the absolute minimum value and the absolute maximum value of g on the interval -4 of x going to 12, and then we need to justify exactly why. Okay, very good. So because of that, we can go and take a look as to what that means for us. So absolute minimum and absolute maximum means that we need to then look at some points that could mean that for us. So again, that's for the value of g, meaning that, again, if the f prime of x, and if the change in sign there, okay, well, that's g prime, so it's g prime of x for change in sign, which in this case is going to be just f of x for ourselves. Right, we're looking for that change in sign, and so that way we can determine if we're dealing with mins or maxes, but we must also take into account the endpoints for the interval. So that means we have to take into account f of -4 and f of positive 12 as possible candidates that we will analyze as well when the time comes. So let's see if our graph of f has any changes in signs that we are looking for. Now, that looks like there's one already at -2, 0. That's a change from negative to positive for the graph of f. Then we have another one at positive 6, 0. That looks like another reasonable one. And I think other than that, that is just about it, because we have two other points here that touch the axis but simply do not change their signs, so is of no use to us. So with that, let's add that to our list of possible candidates here. So we have f of -2 and f of positive 6. So with all these, we should have all the candidates for minimums and maximums. Of course, the largest one being the absolute maximum and the smallest one being the absolute minimum. So we can go and do the work for all of them, and then make our determination on what that will look like. So f of -4, thankfully everything here is on the graph, but that does not mean that that would actually mean anything for us for the function of g, because we are looking for the minimum and maximum of g, not for f. Okay? So in this case, we need to start looking at the values of g. So at g of, in our first case, -4, that would mean we're dealing with the integral going from, the g was already defined before as this integral right there. So going from positive 2 to -4 for f of t dt. That just means with this way that the limits are set up, we want to flip that. So very simple rules here is that by putting a negative coefficient, we can effectively flip the limits so that it will read, in this case, again, reading from bottom upwards is the integral from -4 to positive 2 for this function. Okay, -4 to positive 2 means that we have all of this to contend with. I should switch colors here so that it can be easily seen for all of you. That we are only dealing with this section here, so that's all a negative area, right, going upwards to -2, if that can be seen properly right there. Yep. So that is a triangle that will contain all negative area, and then we have all of this triangle right here leading up to positive 2, 0. So that's where that integral will end. And so with that, we have all that we need to start putting this together. So with that, we have that negative still on the outside. Then we need to determine just area underneath the curve. So our first part is a negative area, this time with a base of, looks like -2 multiplied by a height of, let's see, a height of 4. Yep, that's a 4, but it's a triangle, so I'm going to see multiplied by 1/2 as simply the rule for that. And then we need to add in the positive area, this time of a base of still 4, and then a height of 4 as well, and then 1/2 as the rule for the triangle. So we just need to start working through the algebra on this. So negative on the outside. The 2 times 4 times 1/2, that will be a -4. And then we need to add that with a positive 8. So because of that, g of -4 will give us a result of, now -4 plus 8 is a positive 4, but with the negative coefficient makes it back to a -4. Should be pretty easy to record down as one of the possibilities there. Okay, then going forth, we need to then do g of, in this case, the next one, let's do the next one in order here. So g of -2. So in this case, it will start out as 2 to -2 for the function. But as before, we don't like that ordering. We want to go from smallest to largest on the limits. So we slap a negative on the outside. It goes from -2 to +2 for that function. Okay. So in this case, this will make our life a little bit easier because we already solved a part of that. As you can see, that from -2, let's make sure we have that all right in the center here. So from -2 all the way to +2, right, that is the part that has already been solved for earlier. So because of that, we can go right back to our problem here and piggyback right off of our previous, again, that's the 4 times 4 times 1/2. That was already done with that end. So that's a negative and then a +8 was the area for that triangle. So -8 will be the result of f of -2. So that is good to hold on to on that side. Then off to the next part will be g of 6. This time the integral will be set up from 2 to 6 for the function of f. Okay. Now this is good. This is already in a form that we do like. So we can then just immediately start solving for the area underneath that curve. All right. And so with that, we can take a look here and see that if we're going from 2 all the way to +6, that's a singular triangle. And looks like it's very identical because that triangle for that graphic and going from 2 to +6 right there, that sort of triangle already has that base of 4 multiplied by the height of 4, and because the triangle we have a 1f coefficient as a result of that area, which ends us with a +8 as a result. Okay, so at f of 6 that we have in the note here, so we have a +8, and hopefully we can fit in this last bit of line of work here at g of +12. In this case, will give us from 2 to 12 for that same function. Okay, so let's look back at the graph again to see what kind of areas that we are dealing with. And so going from 2 all the way to 12, and if we were to take a quick note here with this color to make sure we're looking at the same thing right here, is that we are dealing with this negative area as well. Okay, so we have 2 negative areas we need to deal with, one of which already has the base of 4 and the height of 4 in the negative side, so it's exactly the same triangle just on the negative sense, and then a base of 2 and a height of -4 on the other side. Okay, so this should be very easy to set up given that we have everything we need, because we have that. Let's see here, just a second. This, I really put the volume down on that music in the background, but I don't know, the audio fixing on that is a little bit too loud for my taste. Nonetheless though, we have that +8 that we started with going from 2 to 6 that we had, but then we have that same exact triangle just on that negative sense, so it's -8 and then -4, which would have been half of that triangle that we dealt with earlier, and the 2 times -4 dividing by the 2 makes it back to a -4 on that triangle. So because of that, we get a -4 as a result from 12. Okay, and so that will be just about all that was there for this part. Okay, so because of this, we can go back and take a look at what we have here. We have 2 -4s, a -8, and a +8. Okay, so in this case, we have won out the largest negative, so -8 will obviously be the minimum, and the +8 will obviously be the maximum. Okay, so G has an absolute min at the G of -2, which gave us that -8, and then the absolute max at the G of 6, which was the +8 that was there. Okay, so with that, we have everything that we need to put it all together on our side here. If I can make sure, is that still legible? I would say so. So that is all of our parts that we've answered in part C. Now there is a part D, and unfortunately I took up a bit too much space, so we will need to flip that page over to deal with part D. Or you know what? My OCD is kicking in. So why don't we go ahead and just do part D right onto the packet itself. Right, so we answered part A, B, and C already. Again, do that absolute min and max that we've already did earlier. So we just need to do part D, for which the intervals in which g of x is less than 0 on that side. Okay, so if that's g of x being less than 0, all we would need to do then is to then determine where it will stop for ourselves, right? We do know that the g of 2, again, if given that they gave us that function there already of the integral, that is going to be going 2 to 2 of f of t dt. And that itself is already 0. And that's already one guaranteed 0 on the g. And everything else afterwards will be the parts of the integral that we saw. So if you remember, right, looking at the integral starting from 2, that's what the function g was asking for, right? At 10, again, we have the positive area and the same exact negative area going from that side. And so with that, we can conclude that from here onwards, given that these are all negative area for that interval. So g going from the sides from 10 to 12, that's all less than 0. And the same idea is that this was all from our side. This was all negative area for ourselves, again, because we had to flip going to the other side for this function. Right? If you remember as well, from our previous part, actually, we found, if we can show that, right, that's to be g of negative 4 was already a negative result as well. Okay. So because of that, we have the next interval from negative 4 all the way to positive 2 is also being less than 0. Okay. Now because g of 2 starts going positive after that fact, if we show here, right, because it's all positive area after the fact, g immediately becomes positive because we start at 2. There is no need to flip that integral from our previous work. So it looks like we have two intervals right here, right? So g of x is less than 0 from the interval going from negative 4 to positive 2, as well as 10 to 12. Okay, and nice interval notation should be good enough for the test right here. And so that will be our answer as part D. Good. So that will be problem number 3 complete with all that already written out. So we'll go to problem number 4 and we will see what that looks like over there. Okay. Yes, problem number 4 looks like, if I were to show you, looks like part A needs to be done on this paper because it is a slope field question where we have an actual points that they gave us that we need to draw the slopes for. So let's do part A on this packet. We can refer back to it once we are going through our answers. So we have the differential equation dy over dx is equal to y squared over x minus 1. And we have those 6 points there, right? So 6 points starting from, if we do our coordinates properly, so 0, 0. If we're going vertically up, that is the 0 still on the x, 1 on the y, and then 2 on the y. And then going here, these points start with 2 on the x, 0 on the y, and we climb up the y values like that. Okay? And so because of that, we can then discover what the actual slopes will be like. So for example, 0, 0, we will follow off of the differential equation that was given, the dy over dx. So that we plug in, that'll be 0 squared over 0 minus 1, which is still a nice 0 for us right there. Then continue plug in with the 0 in the x, so that's 1 over 0 minus 1. 1 squared that is, which will still be a 1. So that will give us a negative 1 as a slope. And then lastly, 2 squared over 0 minus 1. That will give us a negative 4 as a result. So because of that, we can fill in those slope lines. So 0 on the 0, 0 will give it flat. Then a negative 1 will look something like this. And then negative 4 will be getting a lot closer to vertical. Should be looking like something along the lines there. Okay. Then 2, 0, if we plug that in, now we have 0 squared on the y side. Then it's 2 minus 1, which will be still a 0. Okay. And then 2, 1, it would be 1 squared over 2 minus 1, which is going to be a positive 1. And lastly, we have the 2 squared over 2 minus 1, which is a positive 4. Okay, some very simple algebra problems for us, at least, to find these slopes. So let's fill that in. So horizontal there, positive 1 there, and a positive 4, which would be all the way up there. Good. So we have all that we need to start this problem. And let's see what the rest will look like on our notebook for this problem. So with the rest of problem number 4, again, we are dealing with that differential equation, dy over dx is equal to y squared over x minus 1. Let's make sure to straighten that out. Okay, so for part B here, it is asking, let y be equal to f of x be the particular solution to the given differential equation. Okay. With the initial condition f of 2 is equal to 3. So it then will ask us to write an equation for the line tangent to the graph y is equal to f of x at x is equal to 2, and then use that equation to approximate, in this case, f of 2.1. All right, very nice. So we got that problem set up for us. We got two things to deal with, right? We have the line tangent, and we need to do an approximation at 2.1. Okay? Line tangent, of course, is that we need the function in the form of y equals mx plus b. Okay? And then at x is equal to 2, they already gave us the point at 2 comma 3 is the point that they have given us for that. Okay? In that case, we need to plug an m into the dy over dx. Again, we're going to evaluate that at the 2 comma 3 point. So we will plug that in accordingly for the x and y spots. So because of that, we get 3 squared over 2 minus 1 on that to show. So it's 9 over 1. So the slope will be a positive 9. Okay. And then lastly, at the 2 comma 3, that means that we must plug in then at a 3 into the y. 9 is the slope. 2 into the x plus b to solve for b. Then we get 3 is equal to 18 plus b. And lastly, b will be negative 15 for that result. So our equation itself will be y is equal to, let's see here, it will be 9x minus 15. Okay. So that is one part of the answer. But we're not done yet. We need to do that approximation. So y is equal to 9 times 2.1 plus, no, that's plus, it's minus 15 as a result of that. And so we can do some very simple algebra. That will be 18.9 minus 15, which is a positive 3.9. Okay, so if to show it in the most accurate form, f of 2.1 is equal to a positive 3.9. Okay. All right, very good. So we have simplified all of that out, and so that will be the correct way to do part B. Lastly here, into part C, it says here to find the particular solution. Solution y is equal to f of x to the given differential equation with the initial condition f of 2 is equal to 3. Okay. So now we must do a good old differential equation or separation of variables for this integration. And that is exactly what I was hoping to see here. So for this guy, we need to then refer this back to an original function here. Again, the y equals f of x form, and they give us that initial condition to then solve for plus c. So why don't we go ahead and do that? So let's separate out those variables. So y squared will be transferred to the bottom. The dx will be transferred over to the top. So we have everything set up the way that they should be. If that y squared will show a bit more clearly like that. Okay. So with this, then we can take the integrals from both sides. Okay, is equal to, oh, what am I doing? That's not correct. Let's try that again. It's supposed to be dy over y squared, and then that's going to be equal to the dx over x minus 1 like that. Okay, so with that, we have both of the variables isolated to their sides. So let's see here. So by doing that, we will end up with a y to the negative 1 power with a negative, keeping in track of all of the integration rules. Again, this is basically a y to the negative 2 power. So we just keep track of exponent rule, and that will result in that. And then we have the natural log of x minus 1, and that's a value plus c. Right? Another integration rule about x minus 1 in the denominator will end up as such without any much of a problem. Now we do need to solve for plus c, so then we will then plug in for f of 2 is equal to 3. So let's have a look. So a positive 3 to the minus 1 power, natural log of 2 minus 1, and then plus c. Okay, so because of that, we have a negative 1/3 is equal to the natural log of 1. Now, thank goodness, because we are not allowed calculators in this part. Natural log of 1 is already a fat 0, thanks to some very simple logarithmic rules. And so our c is equal to negative 1/3. So because of that, we have 1 over y as a result of the natural log. That's the value of x minus 1 and then minus 1/3. Okay, now in order for this to be in the correct form of y equals to the result of the function, we just need to throw everything into the reciprocal. Doesn't have to look the cleanest possible, but still something that we can keep track of quite nicely. Will look like something like this. Okay, and so our initial condition will still be met here, but because of that, we also have the negative, so we slap the negative on the top. So that's a negative right there. So make sure everything is nice and neat. Keep track of all the details, and that will be the result of that. Okay. Yep, initial condition looks like it's still met because of that, so we are pretty good for it. Okay, very nice. So that is part C, and that looks like that is all the parts that we needed to go over for this next section. So we will go over into the corrections, and let's see how well we performed on that. So going back to the great amount of work that was put into problem number 3, let's have a look as to see how we performed there. So going down to problem number 3 here, is that we have, let me switch to the red pen here. So for part A, we have the result of, sorry, excuse me. Yes, we have the result of this being neither a minimum or maximum, because we are, it was negative on both sides. Yep. So answer with the justification is good. Okay, so that will be just 1 out of 1. That was correct for part A. Okay, then for part B, it says here that we have the inflection point at x is equal to 4. That is good. And the justification, of course, is that our work shows that we do cross into a positive into a negative. So that's 1 out of 1 correct there. Okay, and then into part C here, we will note that there is, so the -2 and +6 are also candidates for this. So the table will show that we have 4 values, -4, -4, +12, and then -4, 6 and 8, and then the -2 and -8. So all 4 of them are the candidates. That's good. That's 2 out of 2 points to consider. Oh, well, sorry. That's 2 check marks for us. That's 2 points that are made sure as possible answers to this. Then we would consider all that, and then the answer with the absolute minimum being the -2 and -8 as shown there. That's good. And then the 6 and 8 is also correct as well as the end of our work. So that is all 4 points. Good on that. And then not to forget here is that we did do part D of this problem, of problem 3 on this part, given space. But nonetheless though, the intervals going from -4 to +2 and 10 to 12, those are both good. So that is 2 out of 2 correct for this as well. So with that, not a single point was missed. All 9 will be wow, okay. Part A looks like, let's go back to, I guess because they showed it a little bit differently. There's 2 points here actually. It's a 2 out of 2 question here. But they have the G prime of A, B, C, or D. Oh, wow. Okay, that's very interesting. So this is a very interesting way of them putting this down here. Is that you get 1 point. Let me make a note here. So you get 1 point showing that G prime of X is equal to F of X in any problem. That's something to have a note here, that they want you to show this relationship. That is so important that they'll give you a point if you directly show that in your work. That is part of the grading process. So that's actually could be seen right here. I can actually switch the screen just for a second here to show you all. That, again, this is not part right there. The highlighting is really terrible here. Can I highlight like this? There you go. Yeah, this right here, if you can see that, my highlighting is terrible. Let's see. Let's make sure this is all right here. Hey, hello? And this Firefox doesn't want to help me out over here. Yes, but right there. Okay, so that is a part of the grading criteria. That is not part of A, B, C, or D, because again, they're saying that it needs to be an A, B, C, or D in part of the work for that relationship of G prime of X being equal to F of X, and you get granted a point. This is my first time seeing that in the grading portion of this, but it seems that that's good enough reason to be showing in this problem. And of course, if you go back to our actual part here in the work, I did indeed show that in the very start of the problem here, of course, because that was very important to show. And so looks like I get that extra point there. So that's 1 out of 1 as the, I guess, side part. But that does add up since all that I have looked at and corrected was all correct. So that is another 9 out of 9 points for problem number 3. So I will go ahead and take a note on that at the front of this packet here, just so it's much easier to add up our total values at the end of our session here together. And we can get over to problem number 4. Okay, so problem number 4 here. Also remember to begin with is that we did problem number 4 on the packet itself because it was a slope field. They want us to show that directly onto the graphing part of that. So let's have a look here. So yes, we're having zeros on the 0, 0 and the 2, 0. That is correct. Then the opposite sides of +1 and -1 on those different slopes. And then the near verticals with the positive and -4s there. Looks like that's all good. So 0 slopes and non-zero slopes, that is 2 out of 2 correct for this part right there. I'll take a note of that as well. So part A is 2 out of 2 correct because of our work that we have done earlier. And then going into it, we have part B here. And so they want us to do the actual tangent line equation, which ends up as, if they did it in point slope form, so let me show you. So from here, the actual test paper does it in point slope form. This is exactly what's shown on the paper, but this does equate to that if we just do a little distributive property here, adding the +3 at the end of that distribution. That actually equals exactly what I have on this side. So it is the same equation, just written in a different form. They will give you full points for that. And then that approximation of 2.1 giving us 3.9 as a result is also good. So that is 2 out of 2 correct for that section as well. No issues there. Okay. And then lastly, at part C, we have a lot to contend with here. First, they want to do that separation of variables showing, which is exactly what we did on that part right there, to make sure that if we want to do any sort of integration, all of the y's need to go on one side, all the x's need to go on the other side to run a proper integration. Then the actual antiderivative itself is two parts in which they were looking for. Of course, we did that right there. And then the constants of integration and the evaluation of that, which exactly shown right there. We have that plus c at the end of that. And remember that note that they always say is that you will get a 3 out of 5 if plus c is not there. Now, of course, I like to usually make that joke recurring that without the plus c, I would argue if I were test grade that you deserve 0 out of 5. But they will give you that partial credit. Of course, there is no worry for that for us. That plus c is exactly where it needs to be. So we'll solve for that. And lastly, we get the solution for y, which shows up as exactly this. Yeah, they distribute the negative down into the denominator. It really makes no difference. It's still a proper form of this. And so we have that as well. Okay. Now, they did make a special note about when the solution is valid, but that really makes no difference for us. They did not ask for it. But counting this all up, we did get all 5 out of 5 steps that they asked for in this part. And so, because of that, we do get 9 out of 9 correct on this part as well. Very nice. Looks like we are going a lot better than we have last time on this. So that will be 9 out of 9 correct as well for question number 4. Okay. And so we are approaching our last segment here, our last leg for this exam. And so just remember that, again, all of your any sort of questions can be sent directly through the chat or to that email over there on that left side of the screen, labcoatmath@gmail.com. And any other pressing questions will be answered immediately, as this is just kind of the main event as to part of what we do for us on this channel. Okay, so let's go ahead and get to problems number 5 and 6, and we should just about have that for today in the books. So, going here, if my lovely camera would like to focus you. You see my hand, don't you? Come on now. There you go. All right, very nice. So let's go over to problem number 5. Okay, make sure this all nice and squared away for us. Now I would like to draw this out just because this is a very important question for us. So we have a nice funnel here, okay? And so we have some sort of arbitrary radius and a height. Okay, this is a funnel. Very nice. Okay, so the height, so the total height, right? So height is me 10 inches. Okay, and then so it says here at height of any height h, right? The radius is equal to 1 over 20 multiplied by 3 plus h squared, where the height will be in between 0 and 10. Okay, I will do brackets because it's less than or equal to. So height will be between those two values. Okay, and again, this is also going to be in inches. Okay, so we have a changing level of liquid inside of this funnel, obviously as liquid either pours out from this part right there. So part A is saying that we want to find the average value of the radius of the funnel. Very nice. So we have exactly another topic which I spent a pretty nice amount going over both practice problems and a lecture about in terms of average value of a function. So we have exactly what we need to do this because we just want to find the average value of the radius, which means we just simply have to go and take that part. In this case, because h is going to be our variable in which we are evaluating by, we just take the limits going from 0 to 10 and make sure we have the 10 minus 0 as the coefficient waiting for us on that side, and that will be r in respect to h, again h being the variable that we're talking about. So to clean this up, we are talking about 1 over 10 multiplied by the integral going from 0 to 10 for the radius function, which is 1 over 20 multiplied 3 plus h squared dh. Okay, so we can make ourselves lives a little bit easier knowing that we can kick out that 1 over 20, so it becomes a nice 1 over 200 waiting for us. And so we need to evaluate this from 3h plus 1/3 h to the third power, going from 0 to 10. A very nice definite integral, which should take no problem at all for us to solve at this point. So that will result in that 1 over 200 waiting as a coefficient. And then we have to do our limit analysis of 30 times 10, and then plus the 1/3, and then 10 to the third power. Now, of course, because we have a 0 as a result of the second integral, and we have just h's that are waiting for us inside, we can realize that we are just simply subtracting by 0 at the end of that. Okay, very easy. And so we can keep going with the 1 over 200 waiting for us. And then the result of this is going to be all of 300 plus, now 10 to the third is 1,000, so that's going to be 1,000 over 3 as a result of that. Okay, and then we can finalize everything off. This 300 again is going to be 900 over 3 as a simplification here. So it's 1 over 200 multiplied by 1900 over 3. We can simply cancel out, cross cancel some zeros there as a factor of 100. Very easy for us. And so this will be 19 over 6. I'm pretty sure we can leave it as 19 over 6. The test graders prefer improper fractions, or we can do 3 and 1/6 if we really want a mixed number. But again, this is going to be inches as a result. Again, because this is the average radius, and that will be in inches, using good old average value equations, in which I have talked extensively about in other videos, and we should learn easily by now. Okay, so let's go over to part B here. It says here we want to find the volume of the funnel. Okay, so we already have the total height already, right? So the height of funnel is 10 inches. Okay, but then we also need to know that we are dealing with an actual radius. Again, that's a radius function. And please do not be fooled here, because even though, if you look at the packet, this looks a lot like a cone, as you can see, it's very tiny there. But it is definitely very present that there is that slightest circle there at the bottom, which means it is not mathematically a cone. A cone must be ending on a point and not a circle. So again, this is not a cone. Alright, so we just can't say, oh yeah, the volume, dude, volume must be equal to 1/3 pi r squared h. None of that. Okay, I know it's great that you memorize the cone equation, volume, but that is not the case, because this is not a cone. Okay, why to do a lowercase e? That should be positive e. So cone, I'm doing all caps. Okay, that is not a cone that we are dealing with right now. Okay, we are dealing with something which we will then need to go determine the actual true volume of, okay, at least in terms of understanding this really as a cylinder. Okay, there's a cylinder with a changing radius and a changing height, right? So again, because a normal volume of a cylinder is going to be pi r squared h, okay, that we have seen before. Okay, we would then need to go and convert this instead as more of an integration, because again, this function does change in terms of the radius across the height itself. Okay, and the height, of course, is going to be instead, that is going to be the integral, right, from 0 to 10, right, because that is the total amount of height that this guy goes around. Again, we are going in terms of the height, and that is how we can determine the radius at any given point. Okay, so with that, the volume can be reshaped as pi can be simply waiting as an outside coefficient, because that number is not changing anytime soon. So we will go from 0 to 10. Again, as for the radius function in respect to height, we're going to square that in terms of the height. Remember, the height will be multiplied back into it because we are taking the integral in respect to height. So that is one thing going for us there. So we can then clean this up into something that we can start seeing here. So the radius function is 1 over 20, all of 3 plus h squared, all of that squared. Okay. But no, so that's the radius and all of that squared, including that 1 over 20 coefficient in respect to height. Then looks like we need to do some very nice foiling and squaring here. So we end up with 1 over 400, because that's 1 over 20 squared. And then the 3 plus h squared, we have some very nice foiling to do. Something that should be too hard for nice calculus students here, which would be 6h squared, and then plus h to the 4th power as a result of that. Okay, and then we have some one last coefficients to deal with. So pi over 400 to keep it on the outside for now, going from 0 to 10, and then that's going to be 9 plus 6h squared here, plus h to the 4th dh. That will be the result of the integration after all of our work there. Okay, so let's run the actual integral now. We leave that pi over 400, waiting for its time. But now we run the definite integral. So we have ending up with 9h plus 2h to the 3rd power plus h to the 5th over 5. Some very easy definite integration right there. Going from 0 to 10. Now, from 0 to 10, of course, is the 0 going across will just make everything a nice 0. So we really have only one side of this function to worry about, which would be on the 10. So it'll be 9 times 10. In fact, put into there, and then 2, 10 to the 3rd power, and then 10 to the 5th over 5. Okay. Quite a bit going on there, but something that should be very easily done with just a little bit of careful consideration here. So the power 400 is still waiting, and so we get a 90 plus a 2000, with the 10 to the 3rd being 1000, and then the 10 to the 5th being shown right there. And to the 5th power then means it's going to be 100,000 over 5. Okay. Now something that we can do very easily right now is that we can then put in that 400s just to be able to work things out a lot easier for ourselves here. So we can kick off 2 zeros off both of these guys. Okay. And then the 90 will still be left with a pi times 9 over 40, like that, just like that, and then plus a 20 over 4, and then so that 1000 now over 5 will now give us an easy 200, so it's going to be 200 over 4 like this. Okay, and with that we can then simply go ahead and put everything through here. So I mean, I personally wouldn't want to put things into decimal form on a fraction. That's a bit odd. So we could just simply add everything up here for now. So 9 over 40 plus a 220 over 4. This does give us a whole number though, thankfully. That's gonna, this guy here turns into a positive 55 as a result. So in this case, we get 55 times 9, 55 is 9 over 40 times pi as the volume. Again, that's going to be in inches to the 3rd power. If you want to put this in a improper fraction, well, the 40 will give us basically 220 with another 0. So 220 with another 0 there. And then with the 9 at the ones place. So 2209 over 40 times pi inches cubed. Either of these two should be good. Again, that's just a result of our integration. A little bit of extra work, but nothing too much for us to handle here. Okay, let's go over to part C here. And then it will say here that the funnel contains liquid that is draining from the bottom. At the instant when the height of liquid is h is equal to 3 inches, the radius of the surface of the liquid is decreasing at a rate of 1/5 inches per second. Okay. At this instant, what is the rate of change of the height of the liquid with respect to time? Okay, quite a lot going on there, but should be just about fine for us to put together as to an actual result of the problem. So again, going back to it, we got that funnel. Again, the height and rate are changing. Right? The height will continuously go down from 0 to 10. A rate can be drawn as a function of the height. And so they are telling us that at height is equal to 3, so at a very specific point with the height being a certain value, we have the radius decreasing at a rate of that 1/5 inch per second. Okay, so now they want to find, right, at that moment, what is the rate of change for the height of the liquid with respect to time. So we want to know, again, something to keep track. We have the change in the radius and the change in the height, both respect to time. Ooh, what is that? Yes, it looks like we must do some implicit differentiation because both need to be in respect to time. And we only have one function to relate to. Again, that we call that old function. R is equal to 1/20 multiplied by 3 plus h squared. Oh yes, this guy looks like needs to be having the entirety of it take the derivative in respect to time. And remember that we have dr and dh both accordingly. Dr, they already told us, in respect to time, which would be 1/5 inches per second. Okay, so with that, we will need to go and do some lovely implicit differentiation, and we will then see what we are looking at here. So again, that radius respect to time that's already done on the left side. The 1/20 is a coefficient, it can stay there. The 3 goes exactly to 0, and then the h squared, though, we have to keep in mind of chain rule, becomes 2 times h times the dh over dt. And chain rule, that 2 coming down, but also the derivative of the height respect to time is also another part that needs to be kept in mind for ourselves here. Okay, and so with that, we have everything we need here. We just, again, are looking for the change of the height respect to time. So we want to find dh of dt specifically. So with that, we can easily then start doing some easy algebra here to multiply the 20 to the other side and then divide by 2h to then isolate the dh over dt. Okay, some very simple change ups here. This will simplify to a positive 10. So dh over dt in this case is going to be 10 over the height, and they gave us the height already. A height is equal to 3. Okay, so 3 plugged in for the h, and then the dr over dt they told us already as well is 1/5. Okay, so 10 multiplied by 1/5, that will then cancel out to a 2. Looks like we have 2/3 in terms of the inches per second, because that is exactly the units for the height, still in inches, time in respect to seconds. That would be the change for the dh over dt that they have asked for. All right, I'd say that's pretty satisfying. We'll see what that looks like when we get to after we finish our problem number 6 and see what the answers really are. So again, that was problem number 5. We have one more to go, and then we'll go and see what that will look like in our corrections. Okay, so let's go over to problem number 6. We have a nice big table which I will copy over. We have many different factors here. We have x as our first column here, going into f of x, and then into f prime of x, into g of x, and lastly our last column is going to be g prime of x. Okay, so x's will go from 1, 2, 3, and 6. F of x is going to be -6 on that, +2, +8, +4, 3, -2, +7, +5, 2, -3, 6, and 3, 8, 0, 2, and -1. Okay, so as context here for the problem, it says here the functions f and g have continuous second derivatives. Okay, the table above gives values of the functions and their derivatives. Yeah, again, at the values of x. So, very easy for us. We can go and see what they want now. Again, the table's already there. It's twice differentiable, which is nice. They already gave us some values for the first derivatives for both of these guys. So, for problem A, it says here, let this new function k of x be equal to f of g of x. Okay, and then next they say write an equation for the line tangent to. Let's do the graph of k at x is equal to 3. Okay, very nice. So if we want to do a line tangent at x equal to 3, we still need to know the k as well, right? So at k of 3, if we want to do a line tangent to the function of k, we then need to then understand that they're asking for f of g of 3 in that case, which starting with g of 3 from the table, g of 3 going down x equal to 3, the g value is going to be 6, and then from 6 the f value is going to be a positive 4. So the coordinate that we will keep in mind is 3, 4 for ourselves when the time comes for us to use that. Okay, if we want a line tangent, that will also mean that we then also need to find k prime of 3. Again, that's going to be equal to the slope for our equation that that's looking for in the form of y equals mx plus b. So because of that, we will then see, well, yeah, we can go either way. I mean, in terms of other cases, we can also do point slope form. So m and then the is me x minus k. Oh, it's h and k, so x minus h and then plus k at the end. So we can do either way, h and k already being the 3, 4. I'll put it both ways so that a will match up exactly to what the guys want on the exam. So in any case though, we still need to find k prime of x to then plug in for the 3. And we have good old chain rule coming in our way because this is an f of g of x, so function in a function, which means we need to do f prime of g of x on one side and then multiply it by the inside of g prime of x. Okay? So with that, we can continue forth with the k prime of 3, which would be f prime of g of 3 and then g prime of 3 multiplied afterwards. Okay? So very simple plugging in here will then result in some nice answers. So g of 3, if we see on our table, is going to be still a 6. So that's f prime of 6 on one side, and multiply that with the g prime of 3, which will be a positive 2 from there. Okay. So, and then f prime of 6 going down the table is a positive 5. So positive 5 times 2 is equal to 10, which is our slope. So y is equal to 10x plus b. Solving for the b, we plug in for the 3, 4. So 3 goes in place of where the x is. Okay, and so b will be equal to the 4 minus a 30, which is a negative 26. So our first form, minus 26 there, will be that result right there. We can also have it in the form of the x minus h will be minus 3, and then plus k will be plus 4 as a result right there. Okay, both solutions would be able to work. They both satisfy what is being asked for here. So we have that all right there. Okay, either would work. So this is in either case. Just to show you that the test practitioners do not really care about the form, at least it's an acceptable form, either slope intercept or point slope, either would work. Okay, let's go over to part B. It says here, so let h of x be equal to g of x over f of x. So then find h prime of 1. oh boy, we have ourselves a nice quotient rule to deal with, because of course h prime of x is going to be dealing with a quotient rule for this type of problem. Okay, so h prime of x, right, we have to go back to our good old friend, the quotient rule, which will be the low multiplied by the derivative of high, subtracted by the high function g of x multiplied by the low, which is f prime of x, okay, and then f squared of x waiting for us on the denominator. Okay, then we have to plug in for h prime of 1 then. So that's the f of 1 multiplied by g prime of 1 minus g of 1 multiplied by f prime of 1 all over f squared of positive 1. So we have a lot of things to start plugging in for, which we need to keep track of back on top of the table that they gave us. F of 1 is a negative 6. G prime of 1 is going to be a positive 8, subtracted by, instead, g of 1, which is a positive 2, f prime of 1, which is a positive 3, all over f of 1 squared, which is going to be negative 6, all of that squared. Okay, all of which are just simply taken from the table, so nothing really surprising there. Now it'll give us a negative 48 minus a positive 6 over a positive 36, which would be negative 52 over 36. The greatest factor between 52 and 36, is that just 4? I think it's just 4. 52 over 4, that's going to be a negative 13, yeah. And then over a positive 9. Okay. And that will be the result of that. Okay. Very easy to follow along on that side, hopefully. And then lastly, we have part C here. They want us to evaluate going from 1 to 3 on this integral here of f second derivative of 2x dx. Now we've got ourselves a real banger on this one, if I do say so myself. Okay. The reason why, of course, is that now this is not just the derivative of any function. This is the second derivative of the 2x inside of there. So yes, we have fundamental theorem of calculus to keep in mind, but we also need to realize that we are dealing with a 2x, meaning that chain rule will apply. So in this case, even before we evaluate any of those limits, we are indeed going back to the first derivative of 2x, but always remember that whatever answer that we get, we must take that derivative and make sure we are corresponding back to our original. And if we were to take the derivative of f prime of 2x, well, that would mean that a 2 factor will be entering out of there. So because of that chain rule factor, we must keep in mind that a 1/2 must be left out there as well. Okay. So going back, we have the result of 1/2 of f prime of 2x, and we're evaluating it from the limits of 1 to 3. Okay. Thankfully, we still have a nice coefficient waiting for us, so we can keep that there for now. And we are now evaluating f prime of 6 minus f prime of 1. Okay. So because of that, f prime of 6, right, we can go back to our table to figure out is going to be a positive 5 minus f prime of 1, which is a positive 3. Okay. And then lastly, that will be a 1/2 times a 2, which in this case, again, our final answer will be a positive 1 as a result of that integration. Okay, and that is all that is for that problem. Problem number 6, which was indeed the last problem on this packet. We still need to go over exactly what that looks like on the answers, and we should then see what our score will look like out of all the points that we could have earned on this section. So let's go back to problem number 5, and let's see how we scored on that. Okay, so let's have a look here. All right, the 200 there. So let's see. First off, right, the integral, that is indeed correct on this part. Integrating on that section here. And then the actual result of the integration does show there. 30 and 1,000 over 3. Yep, 30. 30. Why is it 30 times? Oh dear, it looks like I made a mistake. It should be 30 times 10. It should be just a regular 30 because it's 3 times a 10 on that side. That is unfortunate that I made that computational error. So unfortunately, the last part would not be correct, at least on that sense. Again, the result of the integration was still correct. I still get a point for that. So that is just 2 out of 3 correct. Unfortunately, because of this, this would have been giving me a complete different answer. If we take off that 0, the 1,000 over 3 was exactly correct. But 30 plus 1,000 over 3 instead will then just give me instead, it'll be a 1090 over 200. Or 1090 over the 600 as a result of 200 times 3 as a common denominator. And so that will be the 109 over 60 instead. That should have been the proper result instead. Unfortunate. But we'll see how the rest of this pans out here. So the integrand going here with the pi on that side, this is exactly how we should have set up part B as a result of a changing volume based off of the radius as a function of the height. That's exactly what they wanted us to have. The result of the integration is going to show right here. The 9h, 2h cubed, and h to the 5th over 5, the pi over 400 coefficient with the limits waiting to be analyzed is indeed correct. And then our computation at the end, the 2209 over 40, that is exactly the way that they wanted this to be. So thankfully on this side we got 3 out of 3 correct on part B. Okay. And then lastly for part C here, we have to make sure that we are dealing with the chain rule. Yep, they are looking for this part exactly as to how the chain rule will turn out for the 2h times dh over dt as a result of the derivative of h squared in respect to time. And so with that, we run through these last bits here, and it turns out, let me see here. So, I guess there's a little bit of a technicality here because they say that it is decreasing by 1/5, so that was supposed to be a negative 1/5, making it negative 2/3 inch per second. And I didn't exactly say that it was decreasing, so I would not give myself a point on that one. Need to make sure we're very careful on those aspects. So that is unfortunately only 2 out of 3 correct here. Everything would have been good. That negative was indeed going to be that separation between right and wrong. I would have made the same argument if a student came up to me and said that they should deserve full points. I would argue absolutely not. That negative was indeed very important. The partial credit still stands though. So with 2 of them missing on this part, that will be 7 out of 9 for problem number 5. A little bit unfortunate with the sloppiness of it, but nonetheless though, the main ideas were still there. Just some cleanup had to be done on the results on that. We were getting close to a perfect score, but we'd have to still work on that as time goes on. Okay, let's go over to the last section here of problem number 6 here. Okay, and so with that, we have just some last bits here. So for problem number 6, we have the equation of the tangent. Yep, they did in point slope form. Maybe I should start going over to point slope form instead, because that's exactly the way that they formatted there. But that is exactly still correct. And then the slope they're looking for, the slope of 10, was exactly what they wanted here. So again, doing the derivative and figuring out the slope, both of them are points that they're looking for. So that's 3 out of 3 correct on part A. Going over to part B, we have the h prime of 1 there, so doing the actual h prime differentiation on the quotient rule, and the plugging in is going to be correct. So negative 3 over 2, very interesting how they have that. 2 and 3, 6 squared. That's not 52. Oy. Wow, that is very unfortunate. That's be negative 54 instead. And that is indeed how you get 2 over 3, because 12? No, 9. No, 18. 18, what? Yeah, 18. 18 is common factor. Oh, yo, okay. That's unfortunate, so that's not correct. That's only 2 out of 3 correct for this. That's very sad that a very simple subtraction was evasive from me. That is very sad. Okay. Lastly, we can evaluate for this for part C here. So that second derivative here is going to give us here the 1/2 with the derivative. Yep, that is one part which they wanted us to make sure that we were good about. F prime of 1 and F prime. I am actually getting quite disappointed in myself. The way that this last section, this is meant to be very easy for us. Plugging in the 1 means that it's going to be multiplied by 2. That's be f prime of 2 instead. Oh man, okay, so that'll be 5 minus a negative 2 instead, which makes it a 1/2 times a positive 7. So that should have been the right answer. That is very sad that that was not the case for us. That is only 2 out of 3 correct on that part. It is very unfortunate that there has been some errors on my side, on the computational side, something that many people look to me to do for them. But unfortunately, it looks like there has been some mistakes on this. So that's 2 parts off. So that's 7 out of 9 on this part, unfortunately, for that. So because of that, it will be 7 or 9 out of question 6. Normally, this is this bit of an anomaly for me, because usually parts 5 and 6 for all my previous parts on these practice exams have been the one spot I knew I can get 18 out of 18 points on. But it looks like we only get 14 out of 18. So because of that, we can then tally up a total here. So let's have a look here. So we are 4 off there, and then another 1 off at the 8 out of 9. So these are only places which we got things off, making it a -5 total. So because the 6 times 9 is out of 54 points, so that'll be 49 out of 54. Okay, I am just off that cutoff. So if we were to go back here, let's take a look at a quick look at a percentage here. So this is 49 or 54, and then make it into a percentage here. So that is going to be a 90.74%. Things were looking quite good for us if only we had that, because if I actually kept all of my computations perfect the way it should have been, most likely would have been 53 out of 54 for us. And those last 4 points really did kill the difference for us. It should have been, I'll make even a note for myself, it should have been a 98.14%. So as you can see, even with a lot of the practice that we have gone through, is that we still need to make sure we keep our computations correct. Again, these are non-calculator questions, which means that our work needs to be 100% true to what we're doing. I think a few extra steps to make sure that I am on the right track here, I think would really make the difference here. And I think should actually make our score a lot better. But this is what we're looking at right now, the 90.74 on this. So that is a very sad face for me, because this definitely should have been one that I definitely should have gone at least over 95% on, considering the way that things have been going. But nonetheless, though, I think that will still conclude it. We have finished this entire 2016 packet. So that'll be another one for the books here that will be on our VOD as a recording of this live stream on our on the channel. So again, it can be viewed at any later time. But nonetheless, though, I think this has been a pretty successful stream. I'm sure everyone here would have definitely enjoyed seeing me get a better score. But nonetheless, though, that should conclude for what we have here for today. Again, the email will always be open, the labcoatmath@gmail.com, for any sort of questions you'd like to ask directly. And we will definitely try to see what this will look like on our next time together. So that will about do it, and we'll definitely try to see what we have in store next time. Thank you for watching, and I'll continue to post our next parts of our calculus lectures